Use an element argument to prove each statement in 7 through 22. Assume that all sets are subsets of a universal set U. For all sets A, B, and C, A cross B union C equals A cross B union A cross C. So here we have set equality. We're proving that two sets are equal to each other. And in order to prove that two sets are equal to each other, we need to show two things. We want to show that A cross B union C is a subset of A cross B union A cross C. And separately, we need to show that A cross B union A cross C is a subset of A cross B union C. Now, to do this, what we're going to start with is an arbitrary element from this first set. And we're going to show that regardless of the fact that the element is arbitrary, that element must therefore also be an element of this set. And the same thing for number 2. Now, normally we would say let X be an element of A cross B union C. But this approach is a little bit misleading because if you think about what elements are in the cross products, elements of cross products are themselves ordered pairs. So instead of saying let X be an element of this, we're going to say let the ordered pair X comma Y be an element of this cross product. This is a little bit more accurate as to what the element would look like. It's still arbitrary in the sense that we don't know what those values in the ordered pair are, but it's the arbitrariness that allows us to extend this proof universally throughout the entire domain of discourse. So by the definition of the cross product, X is an element of this first set, and the second coordinate Y is an element of this second set, B union C. We can unpack what this means. By definition of union, Y must be an element of B or Y must be an element of C. Now we have that X is an element of A, and then we have this OR statement. Now, if we consider X as an element of A as this statement P here, and then Y is an element of B or Y is an element of C, can we consider this parentheses Q or R, then we can use the distributive law to say that then X is an element of A and Y is an element of B, or X is an element of A and Y is an element of C. So this means that X is an element of A and Y is an element of B, or X is an element of A and Y is an element of C. Now, by the definition of the cross product, this X is an element of A and Y is an element of B means that X comma Y is an element of A cross B. And we can do the same trick over here to say that X comma Y is an element of A cross C. So we have this ordered pair X comma Y is an element of A cross B, or it's an element of A cross C. And so now we can utilize the union symbol to package this OR operation. And so X comma Y is an element of A cross B union A cross C. This proves the first part. We now need to show the second part. So for part 2, we're going to let X comma Y be an element of A cross B union A cross C. Now, it's difficult to see why this element would itself be an ordered pair since the outside operation is a union. This is a union between two cross products. It's kind of hard to see why this element would be an ordered pair, but I think it helps to go through this proof to show that eventually this element is an ordered pair, and then rewrite this proof by representing this element as an ordered pair. And the first operation that we're going to unpack is this union, since this is the last operation done in this expression here. So by definition of union, X comma Y is an element of A cross B, or X comma Y is an element of A cross C. From here, it becomes much clearer as to why this element here has to be an ordered pair. Because if the element is in one of these two sets, then that element must be in one of these cross products, and elements of cross products are themselves ordered pairs. Now we've run into an OR statement in our proof, which means we're going to need to break this up into cases. Now in case 1, X comma Y is going to be an element of A cross B. We can use the definition of the cross product. X is an element of A and Y is an element of B. The goal here is to show that X is an element of A and Y is an element of B union C. We already have that X is an element of A. We just need the fact that Y is an element of B union C, but we can do that with addition. So by addition, Y is an element of B, and we can do whatever we want here, we're going to want Y to be an element of C as the alternative. So Y is an element of B, or Y is an element of C. Since we have an OR operation here, we can use the definition of union to show that Y is an element of B union C. So since X is an element of A and Y is an element of B union C, then by definition of cross product, X comma Y is an element of A cross B union C. And that's what we wanted to show. We wanted to show that this element is in A cross B union C. The last thing we need to do is we need to consider case 2. This was case 1 where X comma Y was an element of A cross B. Now we need to consider the possibility that X comma Y is an element of A cross C. Now the rest of this proof is going to look pretty much the same as case 1. By the definition of the cross product, X is an element of A and Y is an element of C. By addition, since Y is an element of C, then that means Y is an element of C or Y is an element of B. So this means that by definition of union, Y is an element of B union C. So we have Y is an element of B union C and X is an element of A. Since X is an element of A and Y is an element of B union C, then by definition of the cross product, that means X comma Y is an element of A cross B union C. The point is that no matter what the case is, X comma Y is going to be an element of A cross B union C. And that proves part 2, that if X comma Y is an element of A cross B union A cross C, then X comma Y is going to be an element of A cross B union C, which proves the second part of what we wanted to show. So since the first set is a subset of the second set, and the second set is a subset of the first set, then by the definition of set equality, both of these sets must be equal. Thanks everyone, and I'll see you in the next video.